The man who began our first decade of manned spaceflight would command the mission that would close that decade. Alan Shepard. With him, Stuart Roosa, who would orbit the moon alone while Shepard and Edgar Mitchell explored its surface.
The joke we heard when we came down here was that the command module was named Kitty Hawk in honor of your first mission. Are you getting a little tired about all this talk about your age?
Well, you know, the long gray beard does get in my way once in a while. I guess it's pretty hard to avoid that kind of talk. It's no secret that I am that old. And it does, it gets a little unnerving to have to be forced to think about it from time to time. Normally, when I'm not talking to reporters, I don't think about my age.
Have you been, let's say, a bear as a result of being grounded? I wonder, you know, how you've been to live with.
No, I think during the grounding period, I found other things in the space program to occupy my attention.
So that wasn't a difficult time for you?
I didn't say that.
What would you say?
It was difficult for me, for example, in the Gemini days when I was, along with Deke Slayton, we used to alternate as directors of each of these respective flight crews, to be with a crew during the final stages of their training and help them with their policy-making decisions and these kind of things, and take them down and get them suited up and take them to the launch pad and then watch them go away. These sure have been difficult times.
We've talked to some people who have likened you to a Superman, and others who've said you're determined never to grow old, and others who have said whatever you're assigned to do, whatever it may be, you can do it, and others who've said you don't like people very well, you don't need them very well. What really is there about you, do you think? Who are you?
Well, who am I to decide? I don't know. You know, a person can't analyze himself. It's important to me to do this because of the self-satisfaction involved. I think everyone needs this sort of thing. And I suppose that's really who I am, an individual who likes to make a contribution to his country because he knows he can with a certain level of confidence. Perhaps that's the easiest way of putting it.
Yeah, I think there's something different about Al. He's probably one of the most talented people in our business that I've come across. You know, he's extremely cool and from a flying standpoint, you know, and he's always right to the heart of the problem.
Al has a responsibility for the overall success of this mission as far as the crew is concerned. He exercises it well, but he allows Stu and I to do our jobs and do them to the best of our ability. And so I haven't seen any temperament that you talk about.
The outcome of Apollo 14 and the remaining Apollo lunar missions will have a great effect on the future of manned spaceflight. If we come through, all of us, with flawless textbook flights, then Skylab, the Space Shuttle, and future manned programs are going to have an easier time getting off the ground. Remember, fewer workers mean increased responsibility for each of you. So let's get with it. Our future depends upon what you do today.
Of course, we're dependent on you, the members of the checkout and launch team at KSC, to guarantee us a safe, flawless launch and flight aboard Apollo 14. That means every functional component of both the Saturn and Apollo checked, tested, and operating as designed.
Their destination, a rugged area of lunar highlands called Fra Mauro. Apollo 13, aborted as it neared the moon, had been unable to land at this site. Now, we were trying again. But why Fra Mauro?
The particular objective is a highland landing, except for the plains, which we had in 11 and 12. We're going to go now into the mountains and look at a different area. We hope to go back to a rather large crater, one which we have nicknamed Cone Crater, and to do our geology traverse in that area, which we hope to pick up some of the original or basement rock that comes from this area. We again, of course, are trying to pin down the causes and the formation of this particular area on the moon, which is called the Fra Mauro region. We have designed our two EVAs for 4 hours of work. We hope to extend that time to 4.5 hours and possibly 5 if we have the consumables to do it, and also if we feel that we are able to accomplish that safely. The amount of rocks that we're going to bring back, we're going to try to expand the weight of them, at least, I guess, well, we hope at least around 80 pounds, even more if we can. And we're going to try to document completely the rocks that we pick up to make it a lot easier for the scientists back on Earth to get a better knowledge of the area and of the material we bring back. One of the objectives, of course, of our lunar flights is to place on the moon scientific packages which have been designed and built by various scientific communities and colleges, universities, and people. We do this to get the most out of our lunar flights. The package is generally called ALSEP, which stands for Apollo Lunar Scientific Experimental Package, or words to that effect. Anyway, the package is basically a group of scientific experiments based around a power generating device and a central station that is capable of taking the results of the of each scientific experiment and sending it back to the Earth by a communication system.
Alert, the guidance system now going internal. 15, 14, 13, 12, 11, 10, 9, 8. Ignition sequence start. 5, 4, 3, 2, 1, 0. Launch commit. Liftoff. We have liftoff with Apollo 14. 3 minutes past the hour. The tower is clear.
Houston is controlling.
Have good thrust on all 5.
16 seconds. Pitch and roll program started. 14 maneuvering to a proper flight course. .25 seconds.
Okay, Houston, roll complete.
Roger, roll complete.
Shepard reports roll program completed. Pitch profile still in progress. 37 seconds.
Stand by for mode 1 Bravo. Mark, 1 Bravo now.
Okay, we're 1 Bravo.
Capcom Gordon Fullerton making that report. Mark, 1 minute. Cabin pressure coming down, adjusting from sea level to a space environment. Status check in mission control, coming up all greens on the flight director's console.
In Houston, everything looks good here on the ground.
Roger.
1 minute, 19 seconds, coming up on period of maximum aerodynamic pressure on the vehicle. Minute 35 seconds, 9 nautical miles in altitude, 5 nautical miles downrange. Velocity now reading 3,340 feet per second. Pass through max Q.
Mode 1 Charlie. Mark, 1 Charlie now.
We're 1 Charlie. EDS auto's off.
Roger.
2 minutes 5 seconds, coming up on center engine shutdown. 2 minutes 12 seconds, 20 nautical miles in altitude.
Inboard cutoff.
Roger, inboard.
Center engine shutdown on time. 2 minutes 25 seconds, 25 nautical miles in altitude, 30 nautical miles downrange. Mark, 2 minutes 35 seconds, coming up on staging.
Cutoff.
Roger.
And separation.
Roger.
Ignition on 5.
Roger.
Head staging, the Shepard crew now riding on 5 good second stage engines.
On 5 engines.
Roger, we confirm good thrust on all 5.
The giant first stage falling away now. It's day's work done. 3 minutes, 10 seconds coming up on skirt sep and tower jettison.
Skirt sep.
Roger.
There goes the tower.
Roger, we confirm the skirt.
The launch escape tower has ejected on top.
Steam press and water auto.
Roger, Ed.
3 minutes, 35 seconds, 14 now 33 feet shorter, 9,000 pounds lighter, moving out well beyond the Earth's atmosphere. We show an altitude of 60 nautical miles. Mark 3 minutes, 55 seconds, 63 nautical miles in altitude, 143 nautical miles downrange, velocity now.
At 4 minutes, trajectory and guidance look good.
14, roger.
And 14, Houston, the CMC is go.
Roger, CMC go.
4 minutes, 20 seconds, velocity now reading 10,750 feet per second and accelerating. In mission control, Apollo 14's trajectory data, driving right down the middle of our plot boards. Right now, flight path data is go. Coming up on 5 minutes, 78 nautical miles in altitude, 235 nautical miles downrange. Retro fire officer reports their 14 is clear of the Atlantic weather. Predicted time for S2 shutdown, 9 minutes, 16 seconds, very close to nominal. We're at 5 minutes, 45 seconds.
Stand by for S4B to COI. Mark, S4B to COI now.
S4B to COI.
Roger, and your times are nominal. Level sense arm 8 plus 3 9er, and S2 cutoff at 9er plus 1 6.
And nominal, here comes.
Capcom Gordon Fullerton reporting that 14 capable of reaching a minimum orbit with a combination of a good third stage and service module engines.
Everything went smoothly during Earth orbit and for the burn that sent Apollo 14 toward the moon. Then Stuart Roosa moved the command module Kitty Hawk to a docking with the lunar module Antares, still attached to the third stage of the booster.
Houston, how's television look to you now? Anything I can do to the picture?
No, I wouldn't change a thing. It looks really good. It's right in the middle and steady.
Okay. The S4B is surrounded here by the typical thousands of, or millions of particles that came out when we separated. They look like little winking stars floating around in a very random pattern. The sunlight is shining very strongly off the top of the lunar module as we drift into it. Stuart's doing an excellent job of sliding in here very slowly. As you can see that our approach speed is a few tenths of a foot per second probably. And the limb is starting to get very large in our field of view, starting to cover the window. Out my plus X window. And the limb, the S4B, are four-sided right on our X-axis. We can see all of the orange, yellow thermal protection around the limb. parts that are black, silver, white. The colors stand out very nicely. We're probably a foot, 18 inches to 2 foot out now.
Roger.
We're at 3 hours, 14 minutes into the flight. We show Apollo 14 at a distance of 6,184 nautical miles.
And we docked.
Roger, we can see a slight oscillation.
Okay, Houston, we've hit it twice, and sure looks like we're closing fast enough. I'm going to back out here and try it again.
Roger.
Twice they tried. 3 times.
3 hours, 17 minutes now into the flight. 14 now, 6,717 nautical miles away.
Well, we better back off here and think about this one, Houston.
Roger.
We're unable to get a capture.
Roger, Ed.
That's Stu Russo and Ed Mitchell reporting that, at least at this point, they're unable to get a capture. We'll stand by.
Okay, Houston, we backed out a little bit, and that last time I hit it pretty good, and we're just not getting the capture latches in there.
Roger, we suggest you verify, if you haven't already, the docking probe circuit breakers on panel 8.
That's verified.
14, Houston.
Go ahead.
We suggest that at the initial contact that you hold plus X for 3 seconds or so at least.
Okay, Houston, we tried it before, but not quite 3 seconds.
Okay.
In space, the astronauts tried a 4th time.
Okay, Houston, I hit it pretty good and held 4 seconds on contact, and we did not latch.
Roger.
As the astronauts waited, an identical docking probe was brought into mission control. This probe on the command module fits into a funnel-like device on the lunar module called the drogue. Tiny catches on the probe's point engage the drogue. It was these capture latches that were not holding.
This is Apollo Control, Houston, 3 hours, 43 minutes into the flight. Troubleshooting continuing in mission control. To quickly repeat, we have been unable to latch with the lunar module. We have quite a while to consider an approach to this problem. The battery power on the S4B is perhaps our major constraining item, allowing us perhaps 6 to 8 hours of time. However, if we're not able to extract the lunar module, of course the lunar landing mission would not be possible. We're at 3 hours, 44 minutes continuing to monitor. We're less than a minute now away from the time of the non-propulsive venting of the S4B.
Ready, mark. It should be on now.
Man, it's beautiful.
We can see one half of it from here.
Okay, I'll back down a little bit and let you watch this.
It's lighting up the whole sky.
Apollo Control, Houston, 4 hours, 47 minutes now into the flight. Pete Frank, over the flight director's loop, advised his ECOM and his flight planning officer to consider procedures for the hard suit if we are unsuccessful in this upcoming attempt.
In space, on Earth, they searched for a solution. Then, on the 6th try,
Hey, Houston, we're on our way in.
We got some, Houston.
I believe we got a hard dock, Houston.
Standing. Roger, Al, that's great.
Super job, Stu.
Thank you.
It didn't even wiggle when he hit it.
It's Apollo Control, Houston. You heard that report. There was a cheer in Mission Control when that report came from Al Shepard. We're at 4 hours, 58 minutes, standing by. We show 14 at 20,700 nautical miles away from Earth.
As they coasted to the moon, the crew brought the probe inside the spacecraft for examination. On Earth, the probe was tested and retested, for we had to be sure that the probe would work for the most critical docking as Shepard and Mitchell returned from the lunar surface.
We are proceeding with every intention of making a full lunar landing mission. With regard to the docking difficulties that we had yesterday, first of all, we did have a successful docking, and every indication is that it was a normal docking. Since that time, as you well know, the crew early this morning took the probe out of the tunnel, and a visual inspection was made. A number of operating tests were conducted. Al Shepard got into the LEM and on the drogue portion and observed Stu Russo as he put the probe in. The capture latches worked normal. From all indications, all the operating parts were operating normally. In addition to that, people have been making extensive analyses here, and we can find nothing wrong with the probe.
The purpose of the excursion into the lab at this time is to check out some of the communications, do a little housekeeping, generally look the vehicle over, and also in this particular case, we're going to take pictures of the command module while we're there. This is done during the flight on the way to the moon to save time so that when we actually go into the lab for the final time, prior to the descent, there will be less things to do. The cabin of both the command module and the lab are extremely clean. We've been very pleased with the way they've looked. Very good. So far, everything is working very well with the command module. We're very pleased with the way the systems are working. Everything is quiet, going along extremely smoothly, and we have a happy little ship here.
On February 4th, Apollo 14 went into orbit around the moon.
Okay, Al, everything looks good down here, and you have a go for LOI.
Okay, we'll give it a go for LOI.
This is Apollo Control. We have had loss of signal as Apollo 14 went around the corner of the moon for the first time.
This is really a wild place up here.
Hey, Fredo, we sure picked a clear day to arrive. There's not much haze in the air at all. We can see all the way to the right.
As Apollo 14 was on its first orbit, the third stage of the booster smashed into the moon at its planned target point. Its impact picked up by the seismometer left by Apollo 12. The structure of the moon's interior is one of the major mysteries of lunar science. Now another piece was added that could help solve the puzzle. Shepard and Mitchell climbed into the lunar module Antares and undocked prior to descent.
And we're free.
Beautiful.
Very good.
But as they checked out the lunar module, a problem appeared. An erroneous abort was being signaled on board Antares and in mission control. Should this occur during the landing burn, Antares would abort automatically, and the landing would be off. The mission control team had 2 hours, the time of one lunar orbit, to find a solution. Flight controller Dick Thorson diagnosed the trouble as a loose particle in the abort button. The burden then came to rest on the shoulders of computer programmer Donald Iles. Working against time at MIT in Cambridge, Massachusetts, he reprogrammed the lunar module computer to ignore the false signal. This new program was then checked out in a simulator at Cape Kennedy. As Antares came into contact with Earth again, the instructions were sent up to the crew.
Antares, Houston, the computer's yours.
Thank you. Your troops did a nice job down there.
That was beautiful.
Less than 10 miles above the lunar surface, Shepard and Mitchell swept across the landing site.
And Antares, Houston, your go for Palmaro.
It's a beautiful day to land at Palmaro.
Then, another problem. The landing radar, which would tell them their altitude above the lunar surface.
On radar. On radar.
Antares, Houston, would like you to cycle the landing radar breaker.
Okay, cycle.
Okay, I would like to accept the radar.
Bridging. Whoa, great. Great. Whew, that was close.
Okay, and monitor descent fuel.
I'm starting the camera. Starting the camera. How much?
10 seconds to go. 4.
Okay, there's pitch over.
64, yes, pitch over, Houston.
There's throw.
Roger.
Right on
And there it is.
Right on the money.
Right on the money.
What's the LPD, Dave?
LPD, 41.
Okay. Back. That is it.
41.
Beautiful.
Right out the window, just like it would be. Great.
Antares, Houston, your go for landing.
Here we go.
Cone Crater,
Okay.
a major objective of this mission to Fra Mauro.
Okay, 2,000.
A hole blasted in the moon's surface eons ago that could provide a scientific clue to the history of the moon, the Earth, and the solar system.
Right on schedule. Right on the
Unclick
down a
left.
little fast.
Unclick left.
2,050 feet a second. A little bit fast, but not bad.
Okay. Outstanding.
Okay, 1,500. Little fast, not bad. Holding in well. LPD's 40 out.
Okay.
Coming through 1,000 feet. 27 feet, right on schedule. Right on schedule now. Going by Cone Crater, right outside to my right.
Okay, the best spot is a little south of track, about halfway between Triplet and Doublet. A little south of track.
Okay.
About 60 meters.
And
That's
it
where
looks
we're
good
going.
from here. Looks good from here. Okay, Al, you're through 550 feet.
Okay.
16 feet per second, 500 feet, 15 feet per second. It looks good. Your fuel is good at 10%.
Okay, let's take it over and move it up a
Okay.
little.
Yeah, I think so. You're through 320
On a half
feet.
hole.
Okay. Okay, I've given it a few clicks. You're through 200 feet. 5 feet per second. That looks good.
No level here.
9% fuel looks great. Okay, looks like you're going right over the middle of triplet. You're 170 feet out, 2 feet per second down, 8% fuel. You're looking good.
Okay, babe.
Okay, 170 feet and holding. About 1 foot per second down. Want to speed it up a little bit.
Yeah, I'm going to move forward.
Okay. Okay, 7% fuel. Okay, you're still at 170 feet indicated.
Starting down.
Okay, you can move on forward. You're just barely crossing North Triplet. Barely crossing North Triplet. 6% fuel, okay. 150 feet. There's decent quantity light.
Okay.
Low level.
All right.
And you can land over here. There's some dust, Al. 110 feet. 3 feet per second down. You're looking great. Great. 6%. There's good dust. You're on your own. It's
Starting down. Starting down.
Okay. It says 90 feet. 4 feet per second, 5 feet per second down.
Okay.
Down, looking great.
60 seconds.
Okay, 50 feet down. 50 feet.
We're in good shape, too.
3 feet per second. 40 feet. 3 feet per second. 30. 3 feet per second. Looking great. 20 feet. 10. 3 feet per second. Contact now.
Two, stop.
Great.
Pro. Auto.
We're on the surface.
Okay, we made a good landing.
Roger.
We think that the Fra Mauro area was formed from material thrown out by the impact that created the Imbrian Basin to the north. If this is the case, we could get samples torn out from as deep as 60 miles in the lunar crust. All in all, the Fra Mauro material should contain a great deal of new information about the early history of the Moon, and thus help us to better understand the formation of our own Earth.
5.5 hours later, Shepard left the lunar module to begin the first of 2 explorations.
And on the surface. Not bad for an old man.
Okay, you're right. Al's on the surface, and it's been a long way, but we're here. You know, I can see the reason we have a tilt is because we landed on the slope. The landing gear struts appear to be about evenly depressed.
Roger out.
And moving around, getting familiar with the surface. Surface in which the forward footpad landed is extremely soft. Matter of fact, it's in a small depression. The soil is so soft that it comes up all the way to the top of the footpath. And even folded over the side to some degree. The same is true of the plus Y strut.
10 years later, 114 hours, 22 minutes after leaving Earth,
Okay, we'll move on
Alan
over.
Shepard stepped onto the Moon. 4 minutes later, he was joined by Ed Mitchell.
We can see you coming down the ladder now. Okay, Ed, we can see you coming down the ladder now.
It's very great to be coming down.
Roger, bottom step.
The last one is a long one. Asset check, very easy to do. Little push and just spring right up.
I guess we got there with those lightweight units.
Yeah, sure glad they did too. That's great.
Okay, Al is bringing the S-band antenna around.
Roger, Al, we're watching you.
Positioning.
And Houston, the SWC is in place.
Roger, Ed, at 114 plus 53 plus 48 GET. SWC.
Okay, set her up. Okay. All kinds of freebies in today's simulation.
Roger, we got the boys in the back room working overtime.
Here I have.
When you start using film.
I just started using film now.
Roger, are you on 24?
12.
Roger, 12.
Okay, let me close the hatch. That's not too far. Tell me when I hit the bottom step. Hit the bottom step. I'm on it. Yep. Oh, okay. Look at this DLR cubed. Yes. Okay. And I'm down. Rocket's running.
Roger, out.
Following the tradition of two previous missions, Shepard and Mitchell planted the flag in the lunar soil.
How's this, Bruce? Look okay?
Roger, that's a good site.
Okay. Goes in very easily. It does indeed.
Now you're going off camera to the right. Okay, that's good.
Okay. Take a picture this way and then we'll swing it around so they can see it on the television.
All right. Okay, we can see it.
I think I'm still too close to you. Except for the limb leg. Yep. Okay. And when you finish, you can flop it around so they can see it a little better in the...
Okay, and which magazine are you using?
Okay.
On the Hasselblad?
Indianapolis, Indiana.
Roger, Indianapolis, Indiana, but that was my line.
The TV cable out. Al, watch your TV cable. Thank you. Yes, man, cable both. Got them both. Back up. Try it again. Okay, you're clear. Okay. Ready. Ready? Ready. Okay, got it.
What's the final exposure number?
Give me a good orientation for the flag.
Okay, Ed, if you just turn it broadside.
25.
Just turn it broadside to the TV camera with the field to the TV camera right. That is 180 out from that. It'd be better.
Okay, there you go. You get 2.5 on the mag.
Copy, Al. Okay, that's good on the flag.
Okay, Houston. Okay. 16. Nope. Okay.
The next job was to load the Met, a rickshaw-like wagon the astronauts would use to transport their tools of exploration and collected samples.
One of the big factors in lunar exploration is mobility. In Apollo 14, we had the Met, which let us move further afield than the previous two missions. In future missions, we'll use the lunar rover, a sort of moon-going dune buggy. This mobility will mean less time spent in getting from here to there and more time collecting scientific data.
Shepard pulled the Met while Mitchell carried the barbell-shaped package containing an automatic scientific station they would assemble. A station designed to continue broadcasting data to Earth for a year after men departed Fra Mauro.
Okay, Houston, we're proceeding over a very fine-grained regolith. Been described before. Good heavens, that's a deep hole. Going down in a depression. Deep, very deep depression, compared to what it looked like. Roger, you're visible from about the armpits up right now. Nothing like being up to your armpits in lunar dust.
Finding a suitable site to place the scientific instruments was the next order of business.
Camera's running 6 frames per second. Roger.
Shepard and Mitchell now began setting up the automated scientific laboratory.
Or PSD sequence.
Yes, sir. The lights for the sign have been deployed. Okay, up comes the central station, and that's one for the troops on the ground.
Okay, we're watching.
A small nuclear generator to power the array. The central station to transmit data to Earth.
So to speak, flapping in the breeze, I guess that's the foil.
A seismometer to detect and measure activity on and within the moon. A series of 3 experiments to measure charged particles near the lunar surface. An independent experiment to reflect laser beams from Earth, enabling extremely precise measurements of such things as Earth-to-moon distance, the wobble of the Earth's axis, continental drift, and shifts of the Earth's crust. And a mortar to be fired by a signal from Earth sometime within the next year. The impact of its charges would be picked up by Apollo 14's seismometer. As a final exercise, Mitchell used the thumper, a device to explode a series of controlled shotgun-like charges. The vibrations from these detonations were picked up by a series of instruments he had previously deployed.
Back to the LAM and to the LSIP.
Roger, Al.
With the instruments set up and operating, they headed back toward Antares, pausing on the way to collect samples.
Get to careful, you don't put them in the ground. You make consecutive passes up the whole circle, we can tell.
They loaded their 44 pounds of lunar material aboard the lunar module, and after 4 hours and 50 minutes on the surface, climbed back into Antares.
And Houston, Al is starting up the ladder.
Roger, did you get everything in the 1 ETB?
Yeah.
Roger, very good.
As Shepard and Mitchell rested, Stuart Roosa continued his work from lunar orbit. His photographs would have meaning not only to the scientific community, but would have direct bearing on the planning for coming missions. 12 hours, 40 minutes later.
Yeah, it's nice to be out on a sunny day again. Yeah, it's a beautiful day here at Fra Mauro Base. Okay, let's start out that direction and take a look around. Okay, and I'll aim the camera towards Cone.
After loading the lunar rickshaw, Mitchell began the journey to Cone Crater.
We're going to try to put the TV camera in the shade and aim it up toward
The magnetometer now on the mat.
Well, we don't want to tarry too long on that one. We're about 2 minutes behind starting out. And the settings, you can leave them just as they are right now.
Well, okay, we'll aim it up toward cone. It's going to be fairly close to the sun.
Roger.
We'll see what happens. Do you have the image of the sun yet?
Okay, we have a little bit of a glare in there, but we have a picture, Al.
Let me bring you a little further to the right.
Roger, Al. I think we can see the slope, left flank of cone coming in.
Pointing in the direction of a cone crater.
Okay, you're looking at cone.
Roger, Al. We have a little bit of a glare across the center, but in the background we can see the crest of cone.
Okay. It will probably be off the camera to the right.
Shepard adjusted the television camera, then hurried to join his partner.
It's the sharper one in the east-north-south line of about 3 craters. And our traverse supposedly passes right between them. Got it?
Okay, we got you right on the map, Ed.
Probably right here, is it not? It's right over here to our left a little bit, Al. I believe.
Point A, the first stop on the trip to Cone. Here they would collect and document samples, measure the local magnetic field, and take core tube samples from beneath the surface layer.
And you might also comment, Fredo, that they have an appearance here quite often like raindrops, a very few raindrops have splattered the surface. It gives you that appearance.
The quality of the scientific description by the astronauts could be termed by Earth-based scientists only as excellent. But now Shepard and Mitchell pushed on. After a brief stop at a second survey site, they began their assault on Cone Crater, a climb not only toward the summit of a lunar mountain, but back through time.
A large crater acts in many respects like a drill, throwing out material from deep beneath the surface. This material should be very different from any we've collected before, perhaps dating back to the origins of the moon and even the solar system.
And we're starting uphill now. Climb's fairly gentle at this point, but it's definitely uphill. Why don't we pull up beside this big crater? Okay, take a break, get the map, see if we can find out exactly where we are.
The maps they were using had been made from photography from lunar orbit. The hummocks, craters, ridges, and boulders took on a new appearance when seen from the surface.
The little limb looks like it's got a flat over there the way it's leaning. Start on up toward the rim? Yeah, just 1 second though. Hey, pull a while out. We're having all the fun. And the grade's getting pretty steep. Al's got the back of the mitt now, and we're turning it up. I think it seems easier. Well, I tell you, we're really going to get a panorama. We got a tremendous one here, Houston, already. And we're not quite to the rim. But the rocks and boulders getting more numerous toward the top here. Okay, well, now that's apparently the rim of Cone over there. And we're about almost 2 hours now. That's at least 30 minutes up there. It's going to take longer than we expected.
Now they were working against time, against the oxygen and water left in their backpacks, against the alien terrain. Top a ridge, thinking it's the rim of the crater, and there's another ridge ahead of you.
Well, press on a little further, Houston, and keep our eye on the time.
Okay, and so right now we have a 30-minute extension.
Looks like we'll be approaching the rim here very shortly. Okay, we better reconnoiter here. I don't see a crater yet. Okay.
Standing in a boulder field surrounded by rocks 10 to 12 feet long, the astronauts made their most difficult decision. With the concurrence of Mission Control, they stopped their climb, less than 150 feet from the edge, to begin the more important job of collecting samples.
The crew had no way of realizing they were so close. It was a week after the mission before we determined this by photographic analysis.
While they could overcome the terrain, they could not beat the steady drain of oxygen from their backpacks. In the terms of scientific meaning, the decision not to go on to the rim meant little. In human terms, a great disappointment.
One of these boulders, Fredo, is broken open. They're really brown boulders on the outside. The interface that's broken is white. And there's another one that most of it is white. They're right in the same area.
The white rock is of different composition to the Apollo 11 and 12 rocks. In fact, the chemistry of all the rocks that have been looked at so far is different to those rocks. Potassium and uranium are 10 times higher, which are the sort of values we might expect if the Fra Mauro rocks represent ancient lunar crust, which of course is what we're all hoping.
Again it was time. Time to head back to the lunar module.
Okay, we'll be setting at 22.
Okay, we need a little more to the right now.
Yeah, I'm just setting it up, Fred.
Okay.
Okay, it's 22. How's that look? Two more to the left, just a minute.
Kilo has never been used, is that correct?
Stand by.
Houston, while you're looking that up, you might recognize what I have in my hand is the handle for the contingency sample return. It just so happens to have a genuine 6-iron on the bottom of it. In my left hand, I have a little white pellet that's familiar to millions of Americans. Drop it down. Unfortunately, the suit is so stiff I can't do this with 2 hands, but I'm going to try a little sand trap shot here.
They got more dirt than ball left side.
More dirt than ball. Here we go again.
That looked like a slice to me, Al.
There we go. There's the die. One more. Miles and miles and miles.
After a quick side trip to check on the science station, they loaded the lunar module with samples and data and stepped off the lunar surface.
Preparing to start up the ladder now.
The second expedition had lasted 4 hours and 35 minutes, a total exploration of a record 9.5 hours. 33.5 hours after they landed.
Okay, the abort stage is set. Gas engine is armed. 6, 5, 4, 3, 2, 1, 0. We have ignition.
What a liftoff.
And liftoff.
Roger, ignition.
Booze. Switch over. 10 seconds.
Roger.
Hey, baby. Switch over is good.
We confirm auto ignition.
Steering looks good, Houston.
Roger, you're looking good from down here, Al.
Coming up on 1 minute.
Well.
2, 1, Mark 1.
Mark 1.
542, 931, 3. Targeting is still good. Okay.
Trajectory looks good. We're at 12,000 feet.
3, 2, 1, Mark 2.
H is good. H is right on. H is right on. Pings and X are together.
Okay, steering is good. Pings looks good, Houston.
We copy, Al, and your go from down here. Coming up on 22,000 feet. The steerable antenna tracking very well.
Okay, steering is still good, Houston. Coming up on 3 minutes. 2, 1, mark it.
Marked. 3 minutes. Mark. 4.
4.
Is good.
H is good.
H dot is good. H is good. Eggs are right together.
About 225 to go. Out of plane looks good.
Okay, look here. That's good.
Hey, you can stop your camera if you want.
Okay.
Bye, please.
Half an hour later, Stuart Russo watched their progress from Kitty Hawk.
What are you doing way down there, oh fearless one? You've lost a little weight since the last time I saw you.
Houston, Antares, the station keeping at about 100 feet, closing in a little more for the victims of the service module and command module.
Okay, I shall do a loop later.
Okay, make it smooth.
And around we go.
Show us a little style. Oh, you look good.
There I was at 240,000 coming over the top.
That's our home away from home.
Would you believe 360,000?
Yeah.
Kitty Hawk is doing an extremely smooth loop. We're sitting at 70 feet, watching him go around. He looks very clean.
The inspection complete, Antares and Kitty Hawk moved together for docking.
Apollo 14, this is Houston. Here, go for the docking.
Roger, we got you.
Okay, we captured.
Beautiful, normal docking.
Okay, and we got a hard dock.
Beautiful. A big sigh of relief being breathed around here.
All over the world there is.
You ought to try it from up here.
They transferred the gear from Antares to Kitty Hawk, buttoned up the tunnel, then jettisoned the lunar module. It would crash into the moon at a predetermined spot. Its impact picked up by their seismometer and the seismometer left by Apollo 12 over a year earlier. 149 hours after they left Earth, they performed the burn that broke them out of lunar orbit. And there was one more item, a series of scientific demonstrations in zero gravity, demonstrations impossible to reproduce on Earth.
And the first one of these is the heat flow. It's a heat flow experiment that we've got mounted over here. It'll flip the camera on. And what we have here are various cells, and maybe Al can point them out there, on the radial zone, and inside each one of these zones is outlined here, is a, so of course on Earth under a 1G feel when you eat something, air, so forth.
These trials looked at basic physical properties of matter in zero gravity. Studies that could lead eventually to new materials manufactured in space for use on Earth. During the coast to Earth, there would be time to catch up on sleep, relax, and do all the little things left undone.
For Al and Ed. Cone Crater was your major objective on your second moonwalk. You almost made the rim. How close do you think you got? And do you believe you collected enough rocks and samples to accomplish the purpose of your mission?
I think so. Let me take the first part of it with respect to how close we got. I think we were within perhaps 100 yards, more or less, of the rim. And certainly in a boulder field that was right there associated with the boulders in the rim. I agree with Al. I agree with Al. I think we were within 100, 150 yards. I think the majority of the type rocks we would find at the rim were in the boulder field that we were working. And although it was a disappointment, just as a matter of challenge not to get up there, I think we accomplished the scientific objectives that we went for.
It is hard for us to get a feel for what it was like in the large boulder field. Was it a forest of big rocks higher than you? Could you see any distance? Over.
Well, the rocks that we were in were ranging of different sizes, but they ranged up to 10 or 12 feet in height above us, so at times we were behind rocks that were taller than we were. As far as the mobility is concerned, Ed, you want to talk about that?
Yes, we didn't have a great deal of trouble moving around the rocks. We didn't even have trouble moving the bet around the rocks, except we did have to dodge them, but of course have to be a bit more careful with the bet than walking without it. Our major problem, however, was the undulating terrain, where you simply couldn't see more than 100 to 150 yards away from you and see landmarks. Consequently, we're never quite sure what landmark would appear when you top the next ridge, and we were very surprised when we topped the ridge, approached the ridge, which we thought to be the rim of Cone Crater, to find there was another one beyond it, and that was the beginning of the real problem.
The next question is, tell us about your problems of fatigue, orientation, and visibility, and apply them, if you will, to the longer 7-hour moonwalks planned for Apollo 15.
Well, I guess we didn't realize that we had problems of fatigue and visibility. As far as we were concerned, our only problem was the amount of time allotted for the excursion. I don't know exactly what our heart rates were. Obviously, they were higher than the normal sitting rate, but we still were not operating at the maximum capacity of our backpacks for cooling, nor were we operating for extended periods of time at high heart rates. To us, it was just a matter of working against the clock. I think that we had the capability to go longer from the standpoint of fatigue. I don't believe that we were disoriented or lost at any time at all either. agree with Al. If my previous answer misled you, it was only a matter of context, because given a few minutes to look around, we figured out where we were, but trying to do it rapidly made it difficult. And as Al says, time was our major factor. Given another 30 or 40 minutes, I think we could have reached the top of Cone Crater, covered all of our objectives, and been back in good fashion.
Well, let me add one thing here. I think if we had wanted to reach the top of the crater and do nothing else, that we could have done that within the time period allotted. But I think that the method in which we reverted to, that of collecting rocks from a point not quite near the top of the crater, provided a lot more geologically and gave us a better cross-section of the rocks in the area, and therefore a better chance of getting rocks ejected from Imbrium than had we gone to the crater and back and not collected as many rocks.
We're now at 1 minute 20 seconds after entry, about coming up now on the maximum G forces, 6.2 Gs at this time.
On February 9th, 1971, 9 days after they left Earth, the crew of Apollo 14 hit the atmosphere of their planet at a speed of over 24,000 miles per hour. They hurtled toward Earth, a meteor heading home. On board, 95 pounds of the moon.
Our return to Earth officer has just estimated that blackout will end about 1 second prior to the predicted time at an elapsed time of 3 minutes 34 seconds after entry. That would be about 15 seconds from now.
Apollo 14, this is Houston through Orion 3. How do you read? Over. Okay, 14, now you're coming in loud and a little bit of noise through Orion 3. How'd it go?
Very good. We're right on board. Things are looking good, Bruce. CMC checking real well.
Okay, 14, we copy drug deploy, and we'll turn you over to the recovery forces now. Have a happy landing.
New Orleans, relay. Relay, group. New Orleans, relay, visual. Approximately 130 from the ship, approximately 5 miles. 9 Zulu, relay on station overhead. Ship to 3. Roger, relay. Give me a 2701 and 17266. 2701, 17266. Stand by for flash on third mark. I think that's correct. I can see it through our window.
Astronaut Ed Mitchell reported the second crewman on the way up to the recovery helicopter.
Astronaut Mitchell is approaching the recovery. Yeah, recovery moving up and left. Astronaut Shepard is halfway to recovery. Astronaut Shepard is approaching the hatch.
And as the helicopter touched down on the deck, we had a delighted group of people crowded into mission control here, applauding. Shortly the cigars will be lighted up as the crew steps out onto the deck of the recovery ship, the helicopter landing platform, New Orleans. The helicopter now being towed to the elevator, be taken below deck for the crew to egress and enter the mobile quarantine facility.
The Apollo 14 astronauts waving, obviously glad to be back, glad it's over, looking forward to getting all the way home once again. Alan Shepard, Ed Mitchell, and Stuart Russo.
These are some of the 94 pounds of lunar rocks returned from the moon's ancient hills of Fra Mauro by Apollo 14. They are beginning to tell scientists a story 3.5 billion years old. From them, we are learning about the early history of not only the moon, but other planets as well. The Earth, Mars, even Venus and Mercury.
Apollo 14 has already had a very big scientific impact. The study of the moon and how, for instance, elements and minerals are distributed in its crust will enable us to learn more about the process of crust formation on Earth, leading to a better understanding of the way that certain elements concentrate in the crust.
Extremely important. It relates to the question of why we're fooling around with the moon. It's really that the imprint of history, of solar system history, on the Earth-Moon system is centered on the moon for the first billion years.